I want to try to tell you a little bit about how some of the work that we do is related to these notions of blue sky, blue ocean technologies. My name is Maginn. I'm in the Department of Chemical and Biomolecular Engineering at the University of Notre Dame. And my group has focused for a long time on the use of atomistic level simulations to try to predict and understand how material properties are linked to their chemical constitution and structure. Okay, in a nutshell, that's what we do. And I want to tell you about how that can be applied to molecular discovery in the context of Earth's work. And we use, in addition to molecular simulation, also machine learning methods. And so what I want to try to convince you is that in any industry, materials really drive innovation. The aerospace industry, think about revolutions in planes, materials made a huge difference. In the pharmaceutical industry, where the product is a molecule, you have to have new molecules to cure different diseases and things. Automotive, chemicals, microelectronics, all these things rely on the advances in materials. And I would claim that the HVACR industry is no different. You might think only of refrigerants, but actually there's a whole lot of different materials that go into this whole ecosystem. So we use metals, we use polymers, elastomers, seals, different composites. We have coatings, sealants. We have all kinds of filters, electrical materials. And what I want to focus on here mostly is refrigerants, some lubricants in the sense that they get intertwined with the refrigerants are important. But I want to just talk about how we can use these technologies to think about blue ocean opportunities in the materials discovery area in HVACR. So this is the kind of typical picture you might have. You have a chemist working in a small laboratory and they need a new material. What's the first thing that they do? Well, they open up the Aldrich catalog and they look for what can I order, okay? And this is old fashioned, this is me, that now you just go on the web, but I like the old Aldrich catalog. And that's the sort of known space. So if you look at this blue square, that's the molecular space that I think of as the whole ocean. And what we're doing is when we open up the Aldrich catalog, we're searching in a very small region of very red space because there are maybe thousands of known molecules, but none of them are new. Anybody can order them. It doesn't require any real talent and you can try them out. There's no synthesis, no testing. It's a highly contested space, all right? And so if you're operating in that area, it's very competitive, okay? Well, you might do a little bit better. You might expand your scope to all of the sort of known chemical space. And you can do that by searching on databases like PubChem or ChemSpire. And you might find you will find a lot of more molecules that could potentially be useful. There are millions of molecules in that space. Still none of them are new. Somebody has already figured these things out. You might require synthesis and testing. And so this is where larger companies have an advantage because they have an infrastructure where you might not be able to order these molecules, they're known, but you might have to make them, you might have to purify them, and you have to test them. But this is still a highly contested space, right? There's still nothing new under the sun in PubChem. And in fact, a lot of people think, well, this is all there is under the sun. And in fact, I'm here to tell you, no, that's not the case. There's pink ocean. I think of this as sort of the moving outside of that contested space. And here you're starting to search on the boundaries of the known chemical space. This is where the intrepid explorers maybe are starting to go. And I like to visualize this by an organic chemist at a whiteboard. These molecules may be known or they may be unknown. You might be able to come up with new molecules this way, even dozens of them. But now you have to do the synthesis and testing. Can these molecules be made? If they're made, what are their properties? How do they work? This is a very much less contested area, so that's why we would call this maybe pink ocean. But it requires a lot of infrastructure and it's very expensive to operate in this area. And this is really, I would say, probably where the cutting edge technology of this industry is right now. This is kind of how we make advances. It's very slow. takes a lot of time, takes a lot of really smart people, and it's expensive. What I would argue is that to really move into the blue ocean area, we need to incorporate the latest advances in AI, machine learning, and molecular simulation into this discovery process. So now the molecular search space is much larger. This is huge blue area, much bigger than the little contested red space that we were talking about. So now my chemist doesn't even wear a lab coat anymore. He can just sit down at the computer. And now you can start to generate millions, billions of molecules that nobody has ever seen before. They've never been made. People have never even thought about that. And I will show you in a little bit. You might think I'm exaggerating, I'm making this up. No, the search space, the chemical space is vast. And in 200 years of research, we have just scratched the surface. But now we have tools that can really open up the vast regions of chemical space. And you can kind of think about this as like a funnel. Computationally, we can generate literally billions of molecules. The nice thing is that all the rules are known. There's no new physics here. We know how chemicals bond together. We know all the rules of chemistry. It's just, can we enumerate the different molecules that nature allows to be made? And then we can use machine learning methods to start to narrow those possibilities down. 10 to the ninth is too many for a human being to even comprehend, but computers can handle this easily. So we use computational screening to look for viable candidates. And we start to narrow this down into the thousands. Progressively, we add more expensive and detailed computational methods until we get down into the tens or hundreds of molecules, where now we can go back and talk to our really smart organic chemists who can start to make and test these molecules. Ultimately, experiment is the final arbiter. We have to do experiments. I'm not claiming that you replace experiments with any of these methods. What I am claiming is it gives you many more possibilities of finding the right molecule than just kind of trying to draw them by hand. That we can use artificial intelligence methods to give us much better choices that we want to do the synthesis efforts on. And we can invest our time and energy in a much more intelligent way. So this is the picture of where I think blue ocean materials discovery is going to be. And this is what we're working on in Earth with some of my students and colleagues.